Hi guys, welcome to circle theorem lesson number 2. Suggest strongly that you review lesson number 1 before lesson number 2, because this is where we introduce the topic and lesson number 2 flows smoothly from lesson number 1. We're going to use some of the principles that we demonstrated in lesson number 1 to solve typical problems that you would see on a CXC exam. Here we have a problem where we're asked to find the angles shown in yellow, and as usual we begin by looking at the diagram carefully and looking out for clues. Clues point us towards specific theorems to apply, so once we see a clue we should dovetail immediately to a particular theorem or set of theorems. In this case, our first clue is that we see an isosceles triangle, and of course the isosceles triangle predicts that the base angles as shown there, x, will be equal. Our second clue is that we see that from chord AB we have an angle subtended at O at the center, and we also have an angle subtended at C at the circumference. So we can apply the angle at the center theorem, where angle at the center is twice that at the circumference. So if the angle O is 2y, then the angle at C would be y. Thirdly, we note that we have two parallel lines, AO and BC. Once we see parallel lines as outlined in lesson number 1, we should start thinking of applying the principle of alternate angles being equal, because a Z angle will exist. And here we note the Z angle and the two angles which would be equal. Let us proceed to find the angles shown in yellow. Application of our first theorem, which is that for the isosceles triangle the two base angles are equal. So we are given angle B as 62 degrees, therefore we know that angle A will be also 62 degrees, and the other angle in the triangle will therefore be equal to 50 degrees. Three angles should add to 180 degrees, so we get immediately angle O as being 56 degrees. We move immediately into recognizing that angle O at the center will be twice angle C at the circumference, and therefore angle C is half angle O, or 28 degrees. Our last angle is angle BAC as shown, and to find angle BAC we apply the principle of alternate angles. We note this, that we have a parallel line which results in a Z angle being formed. We already note that one angle is 28 degrees at angle C, and therefore the other angle, the alternate angle OAC, will be equal to 28 degrees as well. And if you note that we quickly move to finding angle, the unknown angle, because this angle plus this angle forms the base angle, which we know to be 62 degrees, and therefore BAC, which is the unknown angle, will be 32 degrees. Or simply subtract 28 from 62 and you'll have the angle 34 degrees. Very straightforward application of theorems, and an ideal example of using the approach of observing, look for clues, applying those clues to particular theorems. Here we have example number 2, where we're again asked to find angles shown in yellow. Once again, review lesson 1, because we're going to be moving fairly smoothly through these problems. Like we said in lesson 1, we expect that each circle problem should take you no more than 5 minutes to solve. Once you adopt an approach where you start by observing, look for clues, and then allowing those clues to point you in a particular direction. Here we have an approach where we recognize that we have a tangent that is given, RPD, and once again the tangent is going to speak to our application of the theorem which says the angle between the tangent and the chord is equal to the angle in the alternate segment. We outlined in detail how to recognize these in lesson 1. And of course we also recognize a cyclic quadrilateral, and the most practical or obvious application of this one is that the opposite angles are supplementary. So let us find the first angle WXP, and we note that we have the angle 68 degrees which is given between WP, the chord, and the tangent RPD, and therefore the angle subtended in the alternate segment must also be equal to 68 degrees as shown. If we use the same theorem, because we also have chord PY, then we note that the angle between PY, the chord, and tangent is equal to the angle that is subtended at X in the alternate segment, giving PXY to be equal to 36 degrees. From our second observation that WXYP is a cyclic quadrilateral, then opposite angles are supplementary. Therefore angle Y plus angle W is 180, therefore angle Y is 94 degrees. This allows us quickly to find the unknown angle shown in yellow as angles in a triangle is equal to 180 degrees, and therefore XBY is equal to 50 degrees. Finally, we're asked to find the angle at D, or PDY, and we note immediately that because angles on a straight line is equal to 180 degrees, if we know the angle XYP as 94 degrees, then this angle is simply the remainder or the supplementary angle, and that is 86 degrees. And from our knowledge that angles in a triangle are equal to 180 degrees, the unknown angle is found simply as 58 degrees. And this is the end of our second example. In our third example, we begin as we have done before, which is to look carefully for clues in our diagram. And here it is, we are given one angle, 68 degrees, and we're asked to determine angles, 4 angles which are shown in yellow. Let us start as usual by looking for clues. Our first clue is we see an isosceles triangle OSU, and that will tell us that the base angles are equal, so we may need to apply that a little later. Our second clue shows us that we may need to apply the angle at the center. That angle at the center, if you notice, is subtended from chord SU, and there's also an angle at the circumference that subtends from that same chord SU, so we may need to apply that theorem a little later. So let us write this down as another clue. Our third clue is that we have 2 tangents, and from our discussions in lesson 1 we know that the opposite angles are supplementary in the quadrilateral that is highlighted here. And our final clue is that since we can use one of the tangents and apply the principle or the theorem which says that the angle between the tangent and the chord is equal to the angle in the alternate segment. Much of this is explained in detail in lesson 1, so please review if you are having some difficulty following us at this point. So let us find first angles R and O. Now notice that we have used our observation that the angle between the tangent R or PUT and the chord SU is 68 degrees. That's the only information, that's the only angle we've been given so far, so we will start there, and we note that this angle must be equal to the angle in the alternate segment, and here we have the alternate segment is angle R, and therefore the angle that subtends from the chord in the alternate segment is 68 degrees, so angle R is 68 degrees as shown. We can immediately deduce from that that because angle O subtends at the circumference, then angle O is twice angle R, and therefore angle O is equal to 136 degrees. Our final task in example number 3 is to find angle OUP, which is this angle here, and angle T, both shown in yellow. Let us start by using our third clue, which is that we have two tangents, and once we have two tangents, recall that the opposite angles in the quadrilateral that is formed between the two tangents and the center, those opposite angles are supplementary. Therefore, angle O and angle T add to 180 degrees and giving angle T to be equal to 44 degrees. And lastly, we have, if you notice, an angle that is formed between the radius OU and the tangent PU, and from theorem it says that the angle between the radius and the tangent is equal to 90 degrees. Therefore, angle OUP is equal to 90 degrees. Very straightforward application of theorems. Like I said before, please review lesson 1 if you're not understanding us up to this point. In our last example, example number 4, we're asked to find the two angles shown in yellow. Let's start by observing our diagram and looking for clues, and there we note that we have two parallel lines OB and the TA, and we expect then to apply the theory of alternate angles, because here we note that we have a Z angle that exists. In our second clue, we notice the isosceles triangle OBT, and of course the base angles are equal. In our third clue, we note that the angle subtended at the center is twice the angle subtended at the circumference at C. Therefore, we can apply this theory which speaks to angles at the center. And finally, we have one tangent, and we can apply the theory which relates to the angle between the tangent and the chord and the alternate segment. So let's just go ahead and apply these theorems now. To find angle C, we use our theory of parallel lines to note that angle OBT, which is this angle, is equal to the angle given, which is 40 degrees. Therefore, we have already found one angle. Using our second observation, since triangle OBT is an isosceles triangle, then the base angle will be equal to 40 degrees. This gives us immediately our third angle, which is at the center, as 100 degrees, since angles in a triangle must be equal to 180 degrees. From this, we move to finding, using the theory which speaks to the angle at the center, to find angle C as half angle O, which is 50. Let us now find angle ATL, as shown highlighted in yellow. To do this, we recognize that the angle between tangent TL and chord BT is equal to the angle in the alternate segment, which is the angle at C, and therefore the angle BTL is equal to 50 degrees. We already know a portion of that angle as 40 degrees here. Therefore, the remainder of that angle, which is unknown, ATL, is equal to 10 degrees. And that's all there is to it. Please review lesson 1, which is a fairly smooth introduction into lesson 2, and it should put you in good stead to solving any problems in circle theorem in under 5 minutes. See you next time.